Okay, so what we want to have a look at now is what we call the expected value or the mean value of a random variable. I guess you could argue the expected value, we use the symbol mu and e of x. Okay, so often we use e of x, the expected value of x, and it's almost like our average. Okay, so if we toss a coin 10 times, we expect 5 heads and 5 tails. If we roll a dice 1,000 times, we expect that about 1/6 of them, or half of them, if you like, would be even numbers. So it's the long run average if we carry out an experiment a lot. Obviously, if we do toss a coin 10 times, we might get 7 heads or 7 tails, it might be disproportionate. But over a long or over many trials, the expected value is what we expect to have happen. So consider a casino is about to introduce a new game. If X is the amount the casino receives each time the game is played, then the probability distribution for X is as follows. Okay, so what this is saying is they get $1. Okay, so the casino gets $1. Okay, this is saying the casino loses $1, the casino loses $5, the casino loses $10. And these are the respective probabilities. All right. Now, why is it important to know? Okay, so an expected value is what we expect to have happen. So I guess really in short, we need to know if the game is viable. Let's be honest, there's a little lesson in gambling for you. No casino, no organisation runs anything unless they expect to make money. Okay. Why would it mean if the expected value was 0.2? So if the expected value was 0.2, that means they make, well, 1 is $1, they make 0.2 of $1, if you like, 20 cents every turn. Okay, that's what it actually means. All right, so obviously they don't, because when you spin the dice, you either make $1, lose 1, lose 5, or lose 10. But on average, they make 20 cents per spin. So yeah, it's worth having. To calculate the expected value, this messy notation, all they're saying is the expected value of E of X is the sum of the values, so that's all that little epsilon means, sum of the values of X times the probability of X. Okay, so for the casino game above, let's just scroll that page back down again. What we're doing is we're doing X times P of X, X times P of X. So in this case, the expected value is equal to -10 times 0.02 plus -5 times the probability that it occurs is 0.06 plus -1 times 0.1. So it's each X value times the probability of that X value occurring. All right, now I'm just going to assume, to be honest, given that's what the answer above was, that comes to 0.2. Okay? So what else are we saying here? For the casino example, consider any function. So our random variable could be a function, and all this is saying is that if that's a function y equals f of x, well then, since x is a random variable, well then the function itself is a random variable. So the probability distribution of y. So y is equal to 2x squared. So what does that mean? So let's start. There's x. There's the probability of x. So let's just copy them down. So -10, -5, -1, and 1. That was 0.82. That's 0.1, 0.06, 0.02. Now y is simply 2 times the x variable squared minus 20. So in other words, -10 squared is 100. 2 times 100 is 200 minus 20 the corresponding y variable is 180. Negative 5 squared is 25, 2 25s are 50, 50 minus 20 is 30, corresponding y variable is 30. Negative 1 squared is 1 times 2 is 2, I get negative 18, and for 1 I also get negative 18. Okay, so yeah, so that's my y distribution. So now if I work out the expected value of y, it is the probability of y, 0.02 times the expected value, which is 180, plus 0.06 times 30, plus 0.1 times negative 18, plus 0.82 times negative 18. Let's work that out, and we get, which equals negative 11.16. So it's a bit harder to give a meaning to that because we don't really know what the function is. So the expected value of that y variable is negative 11.16. All right, so what are the rules for calculating? So to calculate the expected value of a function, okay, it's just the function value times p of x. For example, the expected value of x squared is just the x squared times p of x. And at this point in time, that doesn't make a real lot of sense, but we do work this one out a real lot, all right? The nice thing is if we have a linear function manipulating our variable, well then the expected value is just a times the expected value of the original plus the b value, all right? So let's have a look at this example here. So expected value of x squared. So if you wanted to do that, we could put x squared there, and x squared is negative 10 squared, which is 100, 25, 1, and 1. So therefore, the expected value of x squared is equal to 0.02 times 100 plus 0.06 times x squared, which is 25, plus 1 times 0.1, 1 times 0.82. What's that? So we'll just add them up. That's 20. 625 is 150, so that's 1.5, 0.1, 0.82. So I reckon that's 22.42, I hope. So the expected value of 2x squared is equal to, well, 2 times x squared, so it's just going to be 0.02 times 2 times x squared, which is 200, plus 0.06 times 2 times x squared, which is 50, plus 2 times 0.1 plus 2 times 0.82. Similarly, well, not surprisingly, it's just twice as big, isn't it? That's 40, 300, which is 3.0, 0.2, 1.64, so it's twice the amount, 44.84. So the expected value of 2x plus 5, from that little rule, it's 2 times the expected value of x plus 5. Now the expected value of x, I can't remember, so let's work it out again. 2 times, what's e of x? E of x is just 0.02 times 10 plus 0.06 times negative 10 and negative 5, I should say. 1 times negative 1 1 times 0.82, which I think was 0.2. So that's equal to, so that becomes 2 times 0.22 plus 5, which is equal to 5.44. Okay, so at the moment it's really just going through a math process. These sort of values, it's very hard to give them a significant meaning, apart from the fact that this 0.22 expected value, that tells me the profit we expect to make from every dice, 22 cents for every time we play the game. As part owner of the casino, your share of profits is half the returns minus 2 cents per game. Find the amount of money you would expect to receive per game. So we just spoke about that, wasn't it? Per game, I expect to get back 22 cents less 2 cents, which is 20 cents per game. Half the returns, oops, my bad. So half the returns, which is 11 cents, minus 2 cents, that makes it 9 cents, doesn't it? So let's set that up mathematically. So my would be 1/2 of the returns, which is a half of 22 cents minus 2. So I get 9 cents per game. Now, if the game is played, how many zeros is that? 100,000 times. Well, that's going to give me 100,000 times 9 cents, which is $9,000. That'd be great, wouldn't it? Anyway, so but that's I guess a more practical application of what the expected value is. All right. Now, the variance of a random variable is the spread. So it's the spread of the distribution. So, okay, so we're sort of saying we expect to collect $9,000, but with what sort of certainty can we have? What's the minimum value going to be? What's the maximum value going to be? So the variance tells me that spread, all right? So the smaller the variance, the more likely any given outcome is. So ideally we have a small variance, so I'm more confident that this particular expected value is what I'm going to get, all right? So to calculate the variance, this one here is the formula we get on the formula sheet, okay? But this is one here is the easiest way to remember it. So the variance of x, and it doesn't matter which sort of a distribution we do, we're going to do a few of them, but for variance and standard and expected value, it's the same. Variance of x is the expected value of x squared minus the expected value of x all squared. All right. So similarly, we've got a variance. Okay, since we're squaring everything here, I'll color that in. Since we're squaring everything here, the little a for the linear expression comes out the front to make it a squared. Now, a very, very practical derivation of the variance is the standard deviation. And that's the one that we tend to talk about most. Most distributions are given by a mean and the standard deviation. Our study scores, they talk about a mean of 30 and a standard deviation of 7. So a standard deviation is just the square root of the variance, okay? So, the way we can interpret this, see the little sigma, that's my standard deviation symbol. So what we're saying is mu, which is the mean. So what this says is the mean minus 2 standard deviations to the mean plus 2 standard deviations. We expect about 95% of the data to be within. Okay, so that's what we expect. So if you like, that's a practical application. So within 2 standard deviations, up or down from your mean, 95% of all your data will lie. All right, so let's have a look at a final sort of use of all this. We might run out of room, but we'll see how we go. So find K. So first things first, what do I know? I do know that all of these values here have to add to 1. So since 0.2 plus 4k plus k plus 0.3 has to equal 1, I know that 5k has to equal 1 minus 0.5, so k is equal to 0.1, which means now I can finish off my distribution as 0.2, 0.4, 0.1, 0.3. Just make sure 0.2, 0.4, 0.1, that adds up to 1, so we're good. The mode is the outcome that's the most likely to occur. So it's the one with the highest probability. Okay, so B, the mode has the highest probability, which in this case, the highest probability is 0.4, but that belongs to x equal to 2. So x equal to 2 is my mode. The expected value is equal to E of x, and that's just equal to the sum of x times P of x. Remember, so that's equal to the x value 1 times 0.2 plus 2 times 0.4, 3 times 0.1, 4 times 0.3, whoops, 0.2 plus 0.8 plus 0.3 plus 1.2, which is equal to 2.5. So there's my expected value, which we sometimes write as mu. So for D, the expected value of 2x plus 3 is simply 2 times the expected value of x plus 3, which is 2 times 2.5, which is 5, plus 3, which is 8. All right. Come up here to E, the variance of x and the standard deviation. All right, so I know that the variance of x is equal to the expected value of x squared minus the expected value of x all squared. I've got that one already, I've just worked it out, it's 2.5. So now I need the expected value of x squared. So maybe, just on my distribution, I might put the x squared values, which are 1, 4, 9, and 16, because now the expected value of x squared is equal to, I won't worry about changing, so it's going to be 1 times 0.2 plus, not 2, but 4 times 0.4, 9 times 0.1 plus 16 times 0.3, which is equal to 0.2 plus 1.6 plus 0.9 plus, well, 3 16s are 48, 1 decimal place, so it's 4.8. So we get 1.8, 2.7, 6.7, 7.5, I hope that all adds up to. So therefore, the variance of x is equal to 7.5 minus E of x, which is 2.5 squared, and that's equal to 1.25. So there's the variance. Standard deviation of x is equal to the square root of the variance, which is equal to the square root of 1.125, which is 1.12 to 2. Oh, let's go back. Okay, and now the variance for f, the variance of 2x plus 3 is equal to, well, that 2 comes out the front, but we square it, it's just 2 times the variance of x. 2 squared times, which is 4 times 1.12, which is 4.48. So notice with the variance in our rule that that has no impact, Because remember, the variance is the spread of the data. And all the +3 does, think of all our translations and that, all the +3 does is shift our graph left and right. So it doesn't actually change the spread, it just moves its location. All right. Finally, find the probability that mu is within x is within 2 standard deviations basically of the mean. So what we're saying here, don't forget, let's put a little 1.12, that's equal to sigma. That's my standard deviation. So the probability that, all right, mu was the mean, 2.5 minus 2 times the sigma, which is my standard deviation, which is 1.12. It's got to be less than x, which is less than 2.5 plus 2 times 1.12 is given by the probability of 2.5 minus, or 2 times 1.12 is 2.24. 2.5 plus 2.24. So it's the probability of 2.5 minus 2.24, which is, what's that? That's about 0.26. X, which is less than or equal to 4.74. So now, what does that mean? X has got to be greater than or equal to 0.26. Now, we're looking at a discrete distribution, which means it's whole numbers. So the nearest whole number that satisfies this condition, we would round that normally to 0, but 0 is not greater than 0.26. So the nearest number that satisfies that is 1. And it would normally round up to 5, but again, 5 is not within that domain, so it has to come down to 4. So what is the probability that 1 is less than or equal to x, which is less than or equal to 4? If we go up to our distribution, that's the whole thing. Now, we've been told it should be approximately 0.95. Well, in this case, it's everything, it's 1. Okay, there's a little bit in this exercise. Take your time to work your way through the terminology: variance, standard deviation, the mu symbol, the sigma symbol. Okay, but they're all very new, so lots of practice.